At our first meeting, I reviewed what I could remember of my conscious input of what it is I am conscious of when I say I'm thinking, and we remember we came out with then a development of a conceptual set, and the process of the thinking itself generated a geometry by virtue of the fact that my conscious input was one of dismissing for the moment, holding out irrelevances in respect irrelevant to the set of experiences which I had had that intrigued me, and I wanted to understand what the relationship was, and I therefore would have to hold to thinking about that, and there was a tendency of intrusion of thoughts coming to me as consequence of my probably having asked myself questions on something, and the brain had been searching, coming back with answers. But the point was that my conscious part was holding off momentarily irrelevances to the situation, the constellation that I was concerned with. And having discovered that my conscious part was this holding off irrelevances, I found that the irrelevances fell into two main categories. All the experiences which were too large and too infrequent in any way alter or tune in with the magnitude of relationships I was considering, and all the experiences in my life which were too high frequency, too small to in any way be measurable at the magnitude I'm considering. So that was really a tunable set. And because the experiences were inherently omnidirectional observations, because our Earth is revolving and we are revolving, and we're going around the sun, continual readdressing of our view in many, many directions, then the dismissal of the irrelevance into a macro and a micro group was an omnigeometrical phenomenon, sending them outwardly and inwardly, and there was then a lucid set of stars that were quite clearly relevant to one another, and that lucid set then defined an insideness and an outsideness. They were between the outsideness, the macrocosm, and insideness, the microcosm. And we then found that the minimum number of stars that could define an insideness and outsideness would be a tetrahedron. That is, the 2 points had between this but no insideness, outsideness. 3 points had between this but no insideness, outsideness. Now we have the 4 points. So as we came to a system, and we're looking for the fundamental number of interrelationships of some things that provoked us, we didn't know what other items might be in it. If we only saw 3 of them, there could very readily be a 4th one. So as we began to really dismiss properly, we'd find out which side that 4th one might be, to give the insideness and outsideness. And we found that there were 4 points, but also the 4 points had 6 interrelatednesses. So we have a prime number 3 and a prime number 2 geometry being generated here by the process of thought. And that I developed a great deal more with you on the idea of the tetrahedron then being the minimum system, because I defined a system as an aggregate of events that divided the universe into all the universe outside the system, all the universe inside the system, a little bit of the universe which is a system, which is the defining subdivision. The tetrahedron is the minimum system of universe, and it turned out to be then omnitriangulated. We found that structures are always triangulated. Structure meant triangle, triangle meant structure. There were no other stable polygons. Therefore, tetrahedron turned out to be the minimum structural system of universe. We did a whole lot more exploring, reviewing about tetrahedra, the cheese platonic solids, and the splicing parallel to the faces of them, and discovering that all of them were made asymmetrical by such slicing, with the exception of the tetrahedron. Simply became a smaller but absolutely regular symmetrical tetrahedron, as we sliced parallel to any of its 4 faces. So we found it's the only geometry that could accommodate, whose symmetry could persist as a symmetrical system universe, and yet accommodate alterations, aberrational alterations, uneven alterations. The other geometries could not coordinate such phenomena. So we found that everything was referenced to 4 planes that were subtending the four vertexes of the tetrahedron, so that we were dealing in a basic four-dimensional system. I've made many references since that time coming back to tetrahedron and structures, and we get into then just recognizing late yesterday that in the water people and the mathematics of the water people coming from the Indian Ocean to Babylon to Crete and then to the Ionian Greeks, the possibility that the king's symbol of the hexagon, the six equilateral triangles, and the household or the distaff side using the square somehow indicated that they got into the public domain, general domain, for the first time in history, the mathematics in terms of reference to x, y, z coordinates of the square, but not in relation to the x, y, z, the w, x, y, z of the the four axi of symmetry of the four triangles of the tetrahedron. So that we find dimensionality suddenly then being identified with the previously by society only with perpendiculars to the system, assuming you have to have rectilinearity. But we find then if you can have four sets of perpendiculars to the tetrahedron to symmetry, and this is the only fully fundamental symmetry that's not altered, so that we find that this four-dimensional quality of the tetrahedron makes it possible to model four-dimensional, five-dimensional models, whereas you could not model with cubes anything more than 3 dimensions. Fourth dimension was not accommodated. So that we found that the tetrahedron volume was 1 and the cube was 3 when the volume is 1, so that if you use cubes, you're using 3 times as much space to identify the number agglomeration, and the tetrahedron then seemed to be not only nature's basic, simplest structural system in absolute limit case, but it also then seemed to be the basic unit of quantation, and we found then we were able to identify that with the quantum mechanics with 1 unit of quantum. So I'm now going to develop some more with you today of the synergetic geometry. And our book will be coming out, I was told today, approximately, to be published, I think, the 3rd of April. And the editor of Macmillan's is here with us tonight out in the control room, and it'd be a good idea for him to experience with us a little of the synergetic geometry. I'm going to review quite quickly the hierarchy of values of the synergetic solids, in contradistinction to the lack of being able to have a hierarchy of values when you use the cube as unity and use the edge of the cube as your unit of linear measure. Then you find that the tetrahedron of equal length edge, or the octahedron, or the icosahedron, all the other Platonic solids, their volumes are irrational numbers in respect to the cube. Whereas with the tetrahedron as unity, and the edge vector of the tetrahedron being the diagonal of the cube rather than the edge of it, because it is necessary. The cube does not, as we saw, have any structural stability without the triangulation, and only when you put in the diagonal into the cube do you have stabilization of it as a structure. So that we see then we have to have it's the diagonal of the cube that makes it a structure. So if I consider only hierarchy of structural solids, where the integrity of the form of the solid is actually guaranteed by being properly triangulated, then we find that the volume of the cube is 3, the volume of the octahedron we showed you was 4, the volume of what we call the rhombic dodecahedron, this form here, is exactly 6, and go on to what we call the vector equilibrium. I gave you the bumping one that fills all the space, which was the form of 12 spheres close packed around one sphere. It is the first nuclear array. There is no inherent sphere at the center of a cube. and you cannot get a stable cube made out of spheres until we get to a very high frequency number of those cubes, of the spheres. But we have the first fundamental nuclear system is then the growth of layers of spheres around a nucleus sphere. That gives you then the 12 around one, and the 12 around one gives us then the 12 vertices of the vector equilibrium. This is just to remind us of the fact that the cube does not have any stability by itself. The rubber joints give it a little bit, but that's where you put there's a little triangulation, like triangular gussets in the corners, provided by the webs of the rubber. So it's triangulation made the stand. Here's our vector equilibrium. And here are then the 4 vertexes in the northern hemisphere, 4 down there, and we got then these 6 around the equator. There's our 12. Now, the volume of the vector equilibrium is 20 when the tetrahedron is 1. And it consists then of, you can see the 8 tetrahedron. The tetrahedron goes from this triangular face into its center. There are 8 such triangular faces, so you get 8 tetrahedra in here. That comes from each of these square faces is the cross-section of an octahedron. It's a half octahedron whose vertex is the center. And the octahedron had a volume of 4, so a half octahedron is a volume of 2. And I have 6 of those square faces, so 6 times 2 is 12, plus the 8 tetrahedra, which are a volume of 1 each, and makes a total of 20. This vector equilibrium is 20. And we saw that this really then is the maximum domain of a nucleus. One of the things I started to really search for in the early days of the energetic geometry, it was the following. I said it could be that we might find some patterns in the universe relation to something where there was really specifically a nucleus. I found there was no inherent nucleus in the cube. You just try to take one sphere and put 8 spheres around it for corners, they just fall off. There's absolutely no structural stability whatsoever. So I want to have a nuclear array, and this is the minimum nuclear array. And that began to really intrigue me, and so I said it could be that around a nucleus there are a set of pattern evolvements. As I have progressive layers, for instance, I put on more spheres, where there may be a unique set of pattern experiences, but you may come to a point where they suddenly repeats the early one. There may be a limit set of absolutely unique nuclear pattern interrelationships. And I found that's exactly what happened. I'm going to need to use my board tonight. And we'll have a red nucleus here. And now I'm going to draw myself a hexagon to make this a little easier to do. I could have another then sphere here. Overdone them a little, sorry. Anyway, I have then a hexagon suddenly showing up in here. And this is in a plane 6 around 1. Then I find that you'll see that between these 3 balls here, there's a nest here. Therefore, I can nest a ball on top of that. When I do that, then I overlap this one too much, so I can't get one on here. I can have one, however, in this nesting. This is pretty bad drawing, I'm sorry. But there's a nest in here. So I can have one here, and one here, and one here. 3 balls can nest on top of here and touch each other. You may remember when I have 3 balls on 2 can touch each other, 3 can touch each other, no question about it. That gives you a triangle. Then there's a nest on top. We're going to have a third ball sit on top, the fourth ball. That made tetrahedron. So I'm really reversing now. There's one at the center, and then 3 are on top of it. I'm sitting in those nests. I get 3 on the other side, and they give me then the 12 spheres around 1. But I want you to think about it for the moment just in a plane, and quite clearly, this is a rather stable affair. Doesn't seem to be trying to do anything to us. I'm going to have another layer of balls, though. I'm sorry I'm making such a mess of my drawing. Seems to have been trouble up in this space here. Now, you say, I don't think anything is happening. Just put another row around, that's all. But you find that I put 6 around here the first time. In the second row, if you count them up, you find that there are 12. There's 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12. And so you've added, each time, first I had 6 sets of 1, now I've added 6 sets of 2. So I have really then a basic 6ness around it because it's a hexagon. But I find that because there were 6 in the first row, and there are 12 in the next row, that makes 18 of them around 1. For 6 sets, then there must be 6 sets of 3, because 6 times 3 is 18. So I want to collect these in 3s. So I can do this. Those 3. And then I take these 3 here. That's further. Then I take this 3 here, this 3 here, this 3 here, and this 3 here. You'll find that those are turbining around. You see the turbine action? The minute I put an additional layer then, the first layer didn't try to do anything. With one more layer on this trying to go around. I could have taken, instead of these 3, I could take these 3. If you do, then it must go the other way. But the minute there's a third layer, they have to go somewhere. It sets up a dynamic patterning. There's quite a little difference in the situation. If I have a light, these are transparent spheres. I have a light at the center here, and its relationship to the nucleus, it gets a very beautiful direct lighting, just tangent. But this next ball here does not have the same amount of light coming to it. So that is a unique pattern. I want to introduce different things that are going on here as the second layer comes in. If I put on a third layer, I've got second, now I'll get into a third, you'll find the same thing happens. From here on, it's always turbining. Only a first layer does not turbine or want to go anywhere. It's really a neutral. I then found, if I began to have the balls around, coming around, growing around it in all directions, if I had the 12 on here, then this next layer, I get it filling in. Every time it comes out the same shape, the vector equilibrium. Always has the 8 triangles and the 6 squares. Every time I keep enclosing it, it comes out that way. I don't think we have any models of that here in the room. Now, I found then that we have a ball at the center. It is 0. There's no layers. It's 0. If I call these layers, there's a 0 layer. And then we come to the next one. We have 12 balls, the first layer. Next layer, we get there are 42 balls. And the third layer, there are 92 balls. If I have a fourth layer, that turns out to be 162 balls. My fifth layer is 252 balls. I found no matter how many layers I had, it always ends in the number 2. When I then recognize that this is a decimal system that I'm counting in, the congruence to modulo 10 is called, I have a constant suffix of the 10, so I take the 2 away. That leaves me, instead of the, it gives me a 10, 40. If I just take out 2 and say plus 2 to all of them, then this would be 90, and 160, and 250. Now each one of those is divisible by 10, so I do that. I get the numbers 1, 4, 9, 16, 25. And you suddenly recognize that is first 1 to the second power, 2 to the second power, 3 to the second power, 4 to the second power. So this what's going on here is that I call this then frequency of modular subdivision. F is my frequency, beautifully done. And we find that the frequency, I gave you also something, the physicist has 2 kinds of acceleration when I talked about precession, remember? There's angular acceleration when you're holding on to the ball, it's going around in a circle, and linear when it goes away. The radials are going away, they are the linears, and this is the angular going around like that. Now, whereas in a square system, or an XYZ system, in order to identify any point in geometry, they always have to go follow the lines. You can't take a diagonal. You can't take a diagonal like that. As that you can't. There's no short way. You can't go from point A here to B on the diagonal. You have to go through C. In fundamental analysis, algebraic analysis of any positioning of any points. But in the 60-degree coordination, because you see then the hypotenuse and the legs are never the same, so the angular acceleration would not be the same language as the radial, linear. But and here the linear and the angular are the same, exactly the same size vector, same energy effect. Remember what a vector means. Vector means vector is represents an energy event, and it represents a mass times a velocity in a given direction in respect to observer. There's an axis of observation. We have a special angle. Observer is moving, and the mass then times velocity gives you a discrete length of line. Vectors are not lines that go to infinity. They're inherently limited. So that when I talk about a vector, these vectors in a vector equilibrium, these represent forces of the universe in balance. The tendency to explode, I showed you the other day, being exactly countered by the contractive forces. So that the hexagon had 6 radials trying to explode and 6 chords. The 6 chords are more favorably arranged because it is a chain. There is mass interattraction, so they get in critical proximity end to end, and they hold together, whereas the 6 other try exploding, they're disintegrating, not helping one another. And the other 6 help one another. So that we have then, in the synergetics accounting, a space between 2 balls in closest packing is then a wavelength, and you don't have a frequency until you have at least 2 wavelengths. So frequency doesn't really begin till you get to this layer out here. In other words, frequency doesn't occur until that turbine, or the disturbing quality enters. It is trying to do something. It tries to go somewhere. And so this is frequency. This is, when you get out here, is frequency 2. Second power. So I'm going to then find a point that we have down here. The numbers of balls in any layer in the closest packing of spheres will always be frequency to the second power times 10 plus the number 2. That became really fascinating kind of a matter. There was every layer had 2 balls assigned to the function of being a neutral axis. There were 2 extra balls for every layer to take care of neutral axis of spin. The nature provided that. And then if you ever thought about Victrola record, this part's going this way and that's going that way, two opposite sides, you get the center with nothing going anywhere. There is literally a neutral axis theoretically there, but you've never been able to demonstrate it in 3 dimensions. But in 4 dimensions you can. I'm going to show it you right immediately now. Come back to our model of the vector equilibrium here. And I will have then, I can get, there are 2 balls, let's say, in every layer that can account for it being a neutral axis. And I'm going to take a vector equilibrium like this, and I'm going to, as I said, lower the top triangle towards the triangle on the floor. I'm not allowed to twist. This is the axis here. I'm not allowed to twist the axis. It simply contracts in length. It does not twist. I do so, but the equator goes around. Here you see then the axis absolutely neutralized, and just able to introduce the motions, the equatorial motions. So we were able to also make this model, as you can see later on, where we make these with wheels that are going, so it doesn't have to stop. They can keep on and on and on accommodating, but the center axis is absolutely immobile. When you get in these 4-dimensional systems, one system like this then can latch onto another on the neutral axis without in any way frustrating the motions which they are participating. It becomes an extraordinary kind of accommodation that we experience in our actual life. We've never been able to accommodate in any 3-dimensional model. But a 4-dimensional model is right there. So we find that two-ness is a fascinating matter. Euler, I told you, developing his incredible realization that all visual experiences were reducible to 3 main aspects: the lines, the crossings of the lines, and the areas bound by the lines. Never to be ever confused one with the other, and that in a picture on a polyhedron and face, or a polyhedron itself, the numbers of vertexes plus the numbers of the areas will equal the numbers of the lines plus the number 2. Absolutely infallibly. But if you make a donut, I said, put a core through it, really where we got that axis there, then the numbers, he said, of the vertexes plus the numbers of the areas equal the numbers of the lines. The 2 had disappeared. I don't know why Euler did not identify that with the axis, because Euler has also made one very great what we call structural engineering analysis. Engineering analysis, structural analysis, goes back to Euler. He's the first to develop then the concept of a neutral axis of spin of all systems. And so it's a structural memory, very odd-shaped. If you have to find out what its neutral is for its dynamic, and he knows exactly how he's going to get your bendings and so forth. We find then why he didn't think of the two-ness of his own formula as representing the poles of the neutral axis. I don't know, but he didn't. But I found he had, and therefore it became very exciting to me. I said, I'm going to now always assign 2 of every layer of my balls. So he didn't get in this ball kind of pattern. He didn't get into these layers of closest packed spheres. And closest packed sphere, this way all the atoms are all packed, so it's a very strong and important kind of a pattern to be considering. And hence we're dealing with atoms and we're dealing with the nucleus, and it has an inherent nucleus. No other geometry I know starts with an inherent nucleus. It's the only one. Closest packed and has nucleus. And this in every way conforms to all of our experience with the atom. So that I found then by taking 2 of every layer, they will always then take care of the neutral axis of the system. Therefore, I'd be able to latch on to any other system, and we can keep on accommodating all the kinds of things we do. Now, this was a very exciting discovery. I've spoken about an inherent nucleus. It is possible to get a nucleated cube, but it has to have many, many layers before a sphere tends to come in the center of the aggregation in pure symmetry. You can get a nucleated tetrahedron, and you can get a nucleated octahedron, and they occur very much more early and very much less aggregation than does the cube. There's a hierarchy of behavior going on here. Now, in this particular formula, we're then dealing with the vector equilibrium has a volume of 20, you remember? And also I showed you that going from this closest packed condition, where there is a nucleus, I took this thing and I made it contract symmetrically, remember? All the 12 vertexes work towards common center at the same rate. Remember, it finally gets to be octahedron. They're all doubled up. As all the vectors came towards common center at a constant rate. And as I drop this then, lower this towards the other side, notice these 6 squares begin to change. Triangles can't change. They are structural. Squares are unstable. They do change. We're now at a point where this thing is contracted slightly, but it's at a point where the short diagonal of those diamonds is exactly the same length as this chord. Therefore, you put this in, there are 6 squares, became 6 diamonds, you put in the 6 cross members, and you have your icosahedron. So the icosahedron is a contracted form of the vector equilibrium. It still has the same 12 vertices, same balls, but because it's contracted, there isn't room for the nucleus anymore. It becomes exactly the same phenomenon. One thing, it does not have a nucleus. Or you have compressed the nucleus, but you say you really can't compress that nucleus, so I have to really consider it does not have it. So I find then vector equilibrium is in a sense a vitiated or an empty, unoperated one, and I have an operated one which has a nucleus. This you get in very much the relationships then between our proton and our neutron. So I find then the icosahedron has a volume of 18.51, where vector equilibrium is 20. This 18.51 is a very interesting number because if you take the relative mass, relative weight of the electron in respect to the proton, and it is 1/1851. It's a really kind of familiar kind of a number in here. So this has something, when we get into the icosahedron level, with nothing at its center, it has something to do with electrons. But you could not take the icosahedron and pack them with other icosahedron and fill all space. They will join to one another and will finally produce a geometry to come back to the octahedron. But they make a very wide open octahedron, but they will not make themselves. And we find then they cannot be multi-layered, because not only could they not have a ball at the center, but as you go from the outer layer into this, the collapse, and there's not room for another layer, so they can only be single layer. Icosahedron is always single layer. But it has other qualities that are very close to the same as vector equilibrium. So vector equilibrium has a characteristic of 20ness, and the prime number 5 is in it. Whereas in the octahedron they had the prime number 6, there were 6 vertexes, and there are 4 faces and so forth. Prime number 2 is in there, prime number 3 is in there. But in vector equilibrium you first come to the number 5, prime number 5 is in there. And we find the icosahedron the same prime number 5. It's the pentagon 5 around each corner and so forth, and it is very fundamentally 5ness. That 5ness is in here as a basic characteristic of either the vector equilibrium, and by the way, vector equilibrium I now write this way because I have to keep saying it all the time, so I use that symbol for it. And so this here is really 2 times 5 times frequency of the second power plus 2. There's a multiplicative 2 showing here, and there's an additive 2 with the prime number 5 and frequency of the second power. As frequency of the second power is a very intriguing matter, because we have now layers, something growing around absolutely symmetrically like waves. It's an omnidirectional wave phenomenon, and every wave characterized by, say, the electromagnetic fundamental wave phenomenon, omnidirectional waving, propagation. And in respect to it, we have, remember Einstein's equation for energy, how much energy is locked up in a given mass, and I went into knots and so forth, self-interferences, but the energy, the universe is the physical energy is, the physical universe, physical is energy, and energy is either energy as radiation, unfettered, or mass brought together. So we have energy equals m, that's the brought together side, times this then is modified how much energy is in there by its relationship to this speed of radiation to the second power. Speed of radiation to the second power, because we said that's the rate at which a surface wave grows. That's the second power. Then we come down to the gravitational constant, and we come back again to my friend the second power, which I spoke to you about, this exponential 2 that shows up, which has something parallel to do with surfaces. And we find here is a system growing rationally, beautiful rational number, absolutely in relation to this frequency of the second power, which characterizes both gravity, the gravitation constant, and the radiation constant. It has to be very, very intriguing. As we go on with these kind of numbers, the 12, 42, 92, I'd like you to add up those numbers, 12, 42, 92. Why am I interested in that? Because, incidentally, I'm going to stop for just a minute, double back myself just a little. I'm going to get into a little more discussion about nuclear phenomena. I have one ball is not a nucleus by itself. I'm not going to start triangulation of balls. And here's one ball, and then I'm going to have two balls tangent like that. There's no ball at the center of the group. And I have another ball, and another ball. No ball at the center of the group, is there? I'm going to have another ball. There are balls. For the first time, there's a ball at the center of the group. It's going to be red, nucleus. Now, let me have another layer. This is the center. There's no ball at the center of the layer. I would have another layer. No ball at the center of the layer. So I need to have one more layer. I don't know whether I can really work this or not, but try. And suddenly there's another ball at the center of the layer. So it went no, no, yes. No, no, yes. No, no, yes. It's not yes, no at all. It's a very interesting kind of periodicity. So it was not until we got to here's a frequency phenomena. Just pay attention to this triangle in here. And we have, while you see four balls to the edge, it's a 3 frequency. 1, 2, 3. 1, 2, 3. 1, 2, 3. It's a 3 frequency system. 3 frequency then has a ball of the nucleus. Therefore, as I begin to build up the vector equilibrium, and each edge of the vector equilibrium shows 4 balls, it's a 3 frequency system, and at that level there's a new nucleus showing, but it's not a nucleus because it's just showing on the surface. There's a nucleus at the center of the thing. There's a nucleus on the surface, but it's not a nucleus till it too is equally enclosed with the original nucleus, which apparently always gets 2 good layers of its own. So this one's going to have, so I can get a frequency, 4 frequency, 5 frequency. After I have 5 frequency, I suddenly am really enclosed and have a new nucleus vying with the original nucleus. So we find that this nuclear idea is one that which the first nucleus shows up at the layer, first layer was this, 12, 42, no nucleus. Not until we got to 92 did we have a new nucleus showing. But we said it wasn't one. It too would have to have another layer on the outside of it here. Still isn't a nucleus. It's not really a nucleus till it gets then to this one, and then it suddenly has, now is really enclosed. You see this 92 is in the enclosure point. This number 92 becomes a very important number, and I'm going to take the 12, 42, and 92. I want to add them up. This is not including the ball at the center of the system, it's just the layers. We finally have 6, 146. That's the number of neutrons in uranium, which is chemical element number 92. That gets to be very impressive suddenly. And then to find that you add to the 146, this is 92. There is a matching, always 92ness. There's always a 2ness on the outside of the system. So there's another 92 that comes onto here. That gives you 8 uranium-238. So if you want to make it feasible, you knock out fog. Well, these numbers suddenly get to be very intriguing. There's compatibility with both, accommodating both Einstein's radiation and his and the Newtonian gravitation, which is what Einstein hoped very much. This is your unified field theory suddenly showing up. I want to realize I'm saying these in a really very kindergarten kind of way, but it's the truth. So you imagine how excited I became about energetic geometry, so I began to get into it many years ago. Because I'd like to just recite once more, as a little boy, there are things that I was always being told, never mind what you think, pay attention to the teacher. And I was trying very hard. But the teacher would say things from time to time that, that I couldn't help have some reservation about it. I never forget going to learning first fractions. And we learned all how to manipulate fractions. Everything's going great. And one day the teacher said, I'm going to show you a better way of doing it. We wondered why she didn't give us a better way the first time. She called decimals. So she had a 0.125, that's 1/8, and 0.25 is a quarter. 0.333 goes out the window and over the hill. Every once in a while things went out of the window, the other things stayed in the room. I wonder if she really knew what she was talking about. It didn't seem to me very good classification. So I began to really ask myself a lot of questions, and particularly when it came to geometry, because I love geometry. And she had a point put on the blackboard. She said it doesn't exist. So she went. I said, I'm going to take a number of these points that don't exist, put them side by side, and that makes a line. And said, that doesn't exist. She wiped that up. Then she took a number of these lines, didn't exist, made out of points, and laid them parallel to one another, and got a plane. Said, that doesn't exist. She wiped that out. Then she stacked a number of those planes made out of, that didn't exist, made out of lines that didn't exist, made out of points that didn't exist, up like this. It says it's a cube, now it says exists. So I wonder how you get existence out of non-existence to the fourth power. And so I said, if it exists, I said, how old is it? She said, don't be naughty. And then I want to know how much it weighed and what its temperature was. Because the word existence, these had something to do to me with existing. And in fact, she couldn't identify it. It was an absolute ghost cube of her imagination. Now, I then want to come back to something else I call the dilemma of mathematics and its imaginary phenomena. And we find the mathematician then talking about lines and lines that go to infinity. And from an Einsteinian viewpoint, that doesn't make much sense, because I said he's entirely operational. He's never been to infinity, so he doesn't say that. He found that all energy was in finite packages and seemed to be an aggregate of finites. And he's not talking about any kind of infinity at all. But we find the mathematician got what he called it to me. He tells me a beautiful, a straight line. I said, I'll draw it. And he takes his ruler and the board. He takes that ruler. I looked at it. I said, it's really, really quite crooked. Look, see that chalk is up and down. He said, you're not in the spirit of mathematics. This is just imaginary straight line, absolutely pure. So I said, I don't know how the word imagination comes out of experience. And the word line was invented by me for an experience I was having, either trajectory of leaving some smoke behind, or I'm leaving some chalk behind, or I've taken a chisel and taken something away. I've left a tracery of my action. And those are always going to be very, very crooked. Anyway, the master said, I mean a line of sight. Get straight. Get yourself now a surveyor's transit. I said, all right, we put the surveyor's transit on the sun. I said, just kissing the horizon in the evening. And we find the sun hasn't been there for 8 minutes, so you're looking right around the curvature of the earth. And the master said, you just apparently don't want to get in the spirit of mathematics. You never understand it. So I finally came to a discovery which I find begins to work fairly well. I'm going to take I spoke about Boole the other night, Boole developing his Boolean algebra when you can't find a logical way, take the most absurd way. And you take the most absolute absurd you can get, and you then get something a little less absurd. You gradually get working towards something that might be reasonable by elimination of the absurdities. At any rate, I'm going to take a deliberately non-straight line. Instead of saying I have a straight line, I want to be ever sure of it. So I take a piece of rope, which is obviously curly, it's all twisted. I'm going to take and one of the definitions of straight lines is it never returns upon itself. So I'm going to take the ends of my rope and deliberately splice them together. So I have a most clearly, deliberately non-straight line, either along the local surface or the ends coming together. It is a closed circuit. And I'm going to take that piece of rope, and I find that I'm going to take any two parts of it and put them side like this and put a clamp on it. Then I'm going to massage the rope from the clamp on like this, keep massaging it very evenly. And I come to where it turns around very sharply back in itself. It's a tight little radius, and I keep it pinched for it. And I make a mark, I put a little red ribbon on that turning point. Then I go to the clamp and massage the other way, and come to where it turns around again. And it gets just as close as I can in the middle of that arc and put another ribbon on. Quite clearly, I've now divided the rope into two parts that are fairly reasonably 50 each, about half of the rope. Heisenberg makes it absolutely clear we can never be exact, so that we just only struggle so far. I'm very content that I've taken unity and divided it into approximately two parts. And now I'm going to take each one of those parts between the ribbon and pair them up the same way. And I'm going to get a quarter points. I'm going to do the same way. Keep halving the distance in between points. We're not increasing and multiplying error, we're simply continually locally halvings. So that each one is a reasonably good half. So we get down to 16ths and 32nds and 64ths and so forth. All nice clear marking distinctions so we know which point we're dealing in. Now we're going to go to the wall, and we're going to put up take some nails, and I'm going to put a nail on the wall. This is the wall we're looking at over here. I'm going to put a nail here, and I'm going to ask you to, I'm going to take the piece of rope and put the first marker on here. I'm going to ask you to really hold it nice and tightly, and I'm going to go to the quarter marker, a quarter way around the rope, and I'm going to pull it tautly from you. So it swings at a radius here, and I can put in another nail anywhere I want on that radius. So this distance between this one I know is 1/4 of my rope. Then with the same thing, you're going to come down here, another quarter point, and I can string it any way you want in here, and so I say let's put it in here. So we come should be about over here. So then I'm going to get to another quarter point. I got somebody holding, and I got holding here, so there's a slack piece in here, and I come down to the marker, pull it tautly, and put in another nail. So now my rope is stretched over that, and the rope is got a diamond. It's an equilateral parallelogram. You're very familiar with that, and there's nothing you've learned in geometry that as far as just playing games of lines, that I will not go along with. It's fine. It's equilateral parallelogram. But I have very clearly already marked on here other points. So I'm going to take the 1/8 points. And I'm going to take the rope off of here, off of this nail here, and pull it down firmly. And so the rope is now going to come down to here. And I'm going to take it off this nail here and pull it firmly up like that. It's going to come up to here. We've got now 2 parallelograms, and I can eliminate this one out here. This is the same piece of rope now. It's 2 diamonds end to end. And it's very easy, absolutely all the way through. It's all equilateral parallelograms, holding them absolutely true. Same length between A and B all the time here. Now, there's no trouble at all to do that again. So each time I'm going to have in here, and we eliminate this. Now we got 4 diamonds in a row. Here it goes. In no time at all, we get to 36 and 64 and so forth, we get down where every time I do this, I halve the distance. So what we have now is this baby. And those vertexes again close. But it's always the same length. It's always it's deliberately non-straight line, but it's getting straighter and straighter. By the time you get to the 64th and so forth, almost no time at all begins to look like a straight line. And it gets straighter and straighter. And I have a way of getting straighter and straighter, which the mathematician didn't have. At least I've got a progression towards straighter. He didn't really have any sort of making time to say, I got a better idea of a line of sight or something like that. He didn't have any really methodical way of getting there. But I know it's non-straight. So I'm going to be able to then get a line for the mathematician, which is, I can really prove mathematically, is probably a little finer than any straight line he's ever used. But I know it's deliberately non-straight. Now the physicist, when he wants to get the student feeling wave, we get into quantum and wave, we only want to feel wave. One of the first tricks he does is to put a nail in the wall and fasten a rope to it, and stand over here and you throw a whip into the rope, and it goes to the wall, comes right back and stops. It's a fundamental calculus of wave, comes back where it stopped. Beautiful thing. What's going on here? You then from A, you whip here from A, it goes out here to B and comes right back to itself. It's a wave, see it? Now when he said I meant a line of sight, that is always wave phenomena. This is a line of sight. Now I'm really able to give him, show him what his real line of sight really was. It is a wave. Physics had found no straight line, found only waves, only curves. So I said, Mr. Mathematician, now I'm giving you a tool that is much more reliable for you, but just never kid yourself again, never call a great straight line. It's simply dealing in wave phenomena, and now we can go on to all the geometry you ever did. This is the first time the mathematician really began to be a little friendly with me, because he is not like really being excluded from the experiential club of the physicists. And his salary is very much smaller than the physicists. This brings me then to, I've given you some agglomeration of spheres, and there are many things I would do if I had more models around me, but I'm fairly limited in my choices, things I see, because I see one frequency and so forth, and not agglomeration. I've already done octahedrons and tetrahedrons with you, and you felt those and felt those grow. And you'll find if we take tetrahedra, I do get 4 tetrahedra together but no nucleus, right? If I however then make another layer, I can have a tetrahedron where you see two balls, three balls on an edge with actually frequency 2, and its number of balls are 4 on the top and 6 on the bottom. There are 10 balls. So 6, 10. Then if I have another layer, it gets another 10, it goes to 20. In this layer, however, the 20 layer, when the 20 altogether, this is the 10. There you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's where the nucleus begins to show up again, the 10 layer. So on this surface of the tetrahedron, on each of the 4 surfaces, you see a new nucleus begin to a nucleus was first, because the tetrahedron didn't have a nucleus of its own. I'll then have to put one more layer, and the next layer will have 15 in it, so it goes to 35. No, not 50, yeah. It does have 15. 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12, 13, 14, 15. There's 15 balls in that. When you do then, for the first time, we have a nucleated tetrahedron. So there is a nucleated tetrahedron. And the same way we can get then to how to get an octahedron with a nucleus. Whereas the same formula then for the number of balls in the outer layer of the nucleated tetrahedron, in contradistinction to the vector equilibrium where it was 10 times frequency to the second power plus 2, it comes out 4 times frequency to the second power plus 2. But the 4 is, as the 10 was 2 times 5, the 4 is 2 times 2 times frequency to the second power plus 2. That's the number of balls in the outer layer when it's tetrahedral. When you do it octahedral, the number comes out 4. We have even fine with this. There's a multiplicative 2 here, and I take that out, so that gives me there's a prime oneness. We find tetrahedron coming out, the prime number 1. The octa comes out the prime number 2, and the cube is a prime number 3, and the vector equilibrium in the icosahedron is the prime number 5. These are the first 4 prime numbers of 1, 2, 3, 4, 1, 2, 3, 5 of all numbers, and we find, as we're going to go on here, some very interesting things of the really number. It goes up only to 4. It's really like the 4 of the vertexes of the basic structural system of the universe. We get 4 positive and 4 negative. We get to the number 8. I'm going to try to show you that. I'm sorry we don't have the good pages and the models and everything all printed out, but we will come back with our video. We have all these pages in synergetics, so we'll be able to take pages from synergetics and reintroduce them into the video. May I have your chart then? Wonder if I could sit on here with that. There's a very bright light there, and everybody can see it a little better. You'll find this is the synergetics hierarchy of topological characteristics of omnitriangulated polyhedral systems. And you must remember, when you're talking about the cube, that in order to have a cube, you must put a diagonal in its face. So it has to, they always must be triangulated. These are structural systems. In other words, they're absolutely stable in doing what they're doing. And there are a great many other items on here, but this is where we begin with the vector edge tetrahedron with a volume of 1. The octahedron has a quality of always doubling on itself, which you may remember as I pump this down here. Octahedron seems to occur in double bond always. You see two octahedra congruent one with the other. The more you get familiar with synergetic geometry, realize that this is fundamental for the octahedron, so it occurs twice. It keeps showing the number 4 where it really represents the prime number 2. It doubles itself. And we find then this is this hierarchy, and I'll go through then the vector edge tetrahedron and the vector edge octahedron, the vector cube and so forth, and vector equilibrium. We find then the vector edge icosahedron combined volumetrically with the vector edge cube, where the cube likes to be edged this way. Its number comes out, the two together come out the number 27. And we find all the vector edge octahedron and so forth. These are all beautiful rational numbers. Now what I found that I spoke to you that Euler didn't think to do was to identify the plus 2-ness of his equation with poles. So I find that every system always has every system is inherently, as he himself knew, is rotatable, and there is a neutral axis of the spin of the system. So that you have to have, now two vertexes have to have the function of being poles. So when I take the Euler formulas, which nobody had done, and automatically subtract 2, take out, let's go through some of these. The tetrahedron has 4 vertexes plus 4 faces, equals 6 edges plus the number 2. 4 plus 4 is 8, and 6 plus 2. The octahedron, we have the 6 vertexes plus 8 faces, 14, equal to 12 edges plus the number 2, 14. Or we get to the cube, and it is now triangulated. So it has 8 vertexes, plus instead of 6, they have 12 faces. It's 18, equals then it's 18 edges, the plus 2. We keep coming out all right. Now, what I did was to take all the formulas as given by Euler, and no topologist looking at this recognized some further order in it because they didn't take out the 2 vertexes for spin. But I now take out the 2 vertexes for spin. And that leaves me for the tetrahedron, 2 plus 4 equals 6. And I got 2 taken out for poles. This leaves me 4 plus, an octahedron is 4 plus 8 equals 12. The vector the cube is 6 plus 12 equals 18. The vector equilibrium is 10 plus 20 equals 30. The icosahedron is 10 plus 20 equals 30. Now each one of these then is coming out in even numbers. I find then, because they're all even numbers, I can divide them all by 2. So I try that. So I get, instead of, for tetrahedron, 2 plus 4 equals 6, I get 1 plus 2 equals 3. That's a very simple kind of relationship. 1 plus 2 equals 3. Then the next was the octahedron, and that had been 4 plus 8 equals 12, so I divide it by 2, and I get 2 plus 4 equals 6. Let me write those down. The first one I got 1 plus 2 equals 3. Now I'm getting 2 plus 4 equals 6. Then I get to the cube, and I've got 6 plus 12 is equal to 18, so I said I divide those by 2, and that gives me 3 plus 6 equals 9. We said that 1 plus 2 equals 3, 2 plus 4 equals 6, and 3 plus 6 equals 9. So what's the next one? The vector equilibrium, or the icosahedron, which was 10 plus 20 equals 30. I divide that by 2, and I get 10 plus 20 equals 30, and I get 5 plus 10 equals 15. Now these are very interesting numbers because you find 1 plus 2 equals 3, you couldn't have something simpler. But the next one, 2 plus 4 equals 6, is 1 plus 2 equals 3 times 2. And the next one, 3 plus 6 equals 9, divided by 3, and it's 1 plus 2 equals 3. And the next one is 5 plus 10, divide that by 5, and you get 1 plus 2 equals 3. So we have in every case here, 1 plus 2 equals 3 times tetrahedron is by 1, octahedron is by 2, multiplied by 2, and cubed by 3, and icosa or vector equilibrium by 5, those first 4 prime numbers. We have then, I found there's what I call a multiplicative 2 and an additive 2. There was an additive 2 of the poles for every system in the universe. There was also a multiplicative 2 because there's a concave and a convex. There's an inherent duality of this congruence of an inside system, because concave and convex are not the same. You just have to realize you have a fundamental congruence of a macrocosm and microcosm. There's negative and positive, some congruent there, but you can't separate them. But the concave radiation impinging on concave concentrates the radiation on convex, diffuses it. So, and energy-wise, you find that they're just not the same, yet they're congruent, you can't separate them. So this is what I call then the duality tunus. So we find every system has a duality tunus, and it has a plus tunus of poles for axial rotation. When I take that out, then there's a constant relative abundance for every vertex, 2 faces, and 3 edges. And the only difference there is a prime number, that a tetrahedron is a 1, an octahedron is a 2, a cube is a 3, and a vector equilibrium or icosahedron are a number 5. Now this gets me very, very exciting. And I gave you frequency the other day, then I showed you a series of triangles. The edge reads 2, then you have 4 triangles, the edge reads 3. That edge is frequency. So I have that frequency, second power, and remember it came out all right. It's triangulation. So as we get into any of these, we find they're all triangulated, so simply increase the frequency. So then in addition to the duality tunus of every system, a polarity tunus of every system, that's a plus tunus, the duality tunus is a multiplicative tunus, the multiplicative tunus, an additive tunus, then there's these 4 prime numbers, and everything else is just frequency second power times that frequency, whatever it is. This tells you all about all the structural systems in the universe. And which is very, very exciting, because then you find, because there is a duality, you do have to have the multiplicative tunus. Therefore, you find that for every positive one vertex, you're going to have a negative one in the system, rather than opposite. So I said 1 plus 2 equals 3, but instead of that, I've got to say 2 plus 4 equals 6. That is, quite clearly, all the numbers of points in the universe will be divisible by 2, and for every point in the universe, there are always going to be 3 vectors, because there are always going to be pairs of points. Then you're going to always have 6. I said the other day, then there's 6 basic, because there's 6 vectors always. With every event in the universe, there's 6 vectors. And those are the 6, and each one is positive, negative, so those are minus 12 degrees of freedom I gave you the other day. I want to see how really beautifully these things begin to prove themselves up and down. There's a very swift simplification and great comprehensive accounting as we get into the synergetics hierarchy. Everything coming out rational and whole. I was so really terribly impressed when I was a kid by the fact that whereas the chemistry was always associating in whole, rational, low-order numbers, disassociating these beautiful whole rational numbers, physics was always coming out with irrational numbers. And I felt that what was the root cause was that we were really using yardsticks that were not the logical yardsticks. That we come in the attic window and we were trying to measure all the rest of the windows by the attic window or something. So it just was an unreasonable original story. So I see that man then feeling monological, thinking it's a flat earth. I can understand him making cubes, and cubes were very nice, so they seemed to fill all space. They were building blocks. Tetrahedron wouldn't all by itself, so I had to cast that out. But it was flat earth anyway, so we might as well just try out cubes, and that's the way to divide the universe. The minute you get in the spherical, you're going to realize they're not going to work very nice, but you could have this triangle on the surface, and then it went to the center of the sphere. You get a beautiful tetrahedron right there all the time. This chart goes on to get into really these complex forms that we're getting here. So they're all superbly accounted. You'll never get in trouble. But all of them are some combination of those first 4 prime numbers. That's all you have to have. And the minute you get a 3, you know you're dealing in cubes. That's all it is. It's always going to come out of it.